What did we discuss in the previous class? Yeah, Lagrange multiplier for something we discussed. That was not the key. Support vector machines, linear classification, linear separable classification we have seen. We have looked at the derivation part of it. There we have seen two ways of solving it. The first one is the direct problem that you got as a result of applying Lagrange multipliers. The second one is those so-called KKT conditions, where you take the derivative of it with respect to W bar and with respect to W naught and substitute them. Then your minimization problem turns out to be a maximization problem in terms of lambda. And we also have discussed the pros and cons of each of those approaches, right? By the way, while I was writing the equation, there was a mistake of sign in the last step. There should be, instead of minus, there should be a plus there. If you recollect, there is a summation over all lambda I. The term is there it should be positive. So please make a note of that. Okay. Yeah. Now it's time we move to another type of classification required, this being linear non-separable classification. So earlier, the kind of classification problems we have looked at, maybe why should we always draw like this? Let's draw the graphs like this. So earlier, within these boundaries, there were no feature vectors. That's how we did it. That is fine as long as you have completely separable classes. But there could be quite a few instances. Again, consider feature vectors of x1 and x2. There could be on one side of this was a simple case earlier where you do not have any of the feature vectors in between, but it may so happen that you could get few feature vectors here of this class, and also on the other side there could be an overlap, right? It's not always, things are not always separable in practice. And similarly, you could have some class stuff here, and also on this side some outliers could be there. And of course this feature vector, there might be some points on the feature vector also, but still you want to use support vector machine where you try to minimize the number of points here. If you don't want any points, there is no solution. Okay, like in life, in maths also, you need a optimization problem subjected to some constraints here. So you would allow some points to come there. Now the problem for us is how to formulate this and how to solve this. Recollect the earlier way we solved it. It was pretty clear. You do it. These are such a way that you keep on increasing this distance on one side, and on another side you put a constraint that there are no points in between. But the scenario is different right now. This is let's say omega 1, omega 2, it's up to you the way which you call it. There are some minimal points. Maybe I have drawn too many here or too less here, but consider relatively there are minimal points. One class also, it is a non-separable one. So there could be some overlaps. Okay, some kind of lapses happen here and spillovers are there to the other side. So how do you solve this problem? This is what we are going to do in the, at least for the first part of our class today. Let us see what are all different cases that are possible. I would write here the case 1 being feature vectors are outside the margin. Very straightforward. This has been the bread and butter for us in the previous class. This is what we were doing. So how do you do that? Then what is the condition that it needs to satisfy? xi, yi be the point. So you tell me the condition that we are trying to impose there in such cases. Yi into w bar transpose xi bar, then what? Plus w naught, right? This should be greater than or equal to. Very good. So for those which are the support vectors, this would be 1. For other points, this is greater. Things are pretty straightforward. This we got used to. Now we have 2 more cases here. Can you tell broadly what could be perhaps those 2 cases? Inside the margin, let's call it. And there are 2 cases inside the margin. What are those 2 cases? See again, this is your decision plane. Keep that in mind. This is your hyper decision plane or whatever you call it, or simply decision plane. Now you tell me, how do you classify the feature vectors falling into that margin now? Correctly classified and misclassified. There are 2 ways. Once this line is there, it is okay during your testing. Some points come here, you don't really mind. Okay, that is next best thing to happen. You try to give the maximum space, but on the fly, when people are coming and they are sitting in the right places, there is no issue with that. So let us put the case 2 as feature vectors inside the margin and they being correctly classified. Can you tell me what would be the condition satisfied by them? Which are correctly classified, but within the margin. Can you tell me which is the condition that they would satisfy? Very good. Can it be equal to also? It is a, you can put it on either side. If it is on the decision plane, still you could consider, very few are there. You could, if you want, you can put equal to also there. But essentially, that is also there inside. If you consider that, that will be now yi bar, sorry, yi is not a vector. It's just one output, +1 or -1 here classification. Okay, yi into w bar transpose into xi bar plus w naught is, let me just check what I was writing there. This could be in between 0 to 1. Can I write that? Greater than 1 after multiplication with yi is on both sides. This is 0, this is 1, in between 0 and 1. And of course, I'm just, this can be argued. You could put it the other ways, whether it is correctly or misclassified, but you have to put it, it's like a step function. What will you do at 0? You will give to one of those classes, right? This is what would happen for those points which are correctly classified, right? Because even if, for example, if this is negative here, yi is negative here, this is on this side, it is negative. So after multiplication, it will become positive and vice versa. You could consider this positive, the other way around. yi you will accordingly consider there. Now the last case. The feature vectors are inside and misclassified. In other words, you just tell me in terms of inequality. That's all. It is less than 0. So I could write there yi into w bar transpose into xi bar plus w naught is less than 0. Yeah, earlier situations are far better. You had only one constraint, this constraint. Now you need to accommodate 3 constraints here. So the first thing before we attempt at anything else is to bring all 3 into a generalized constraint. That is what we will attempt now. How will we write that? We will write a generalized constraint where I would say yi into w bar transpose times xi bar plus w naught, okay, plus w naught should be greater than or equal to 1 minus epsilon subscript I. 1 minus epsilon subscript I. To deal with 3 different constraints, I have no other choice than incorporate some other variable here. Now I need to define this variable such that for different values of it, all these 3 conditions are met. That is essentially what I need to do. So how could I do that? Now let's say epsilon I equal to, for case 1, what should be the value of epsilon I? 0. Very good. 0 for case 1. What will be the value for case 2? See this value. Now when will this be 0? 1. Okay, 1 is included. On the other range, when it will be, what is the other one? It can be value up to 1. So what should be the other? 0. So when it is in between 0 and 1, right, then this condition is satisfied. The case 2 condition, this will be, so 1 minus something, as long as the value you are subtracting is in between 0 to 1, this value will be also in between 0 to 1. What is the remaining one? This is for case 2. Okay, then what about case 3? When will this be satisfied? For this to happen, what about epsilon I in that case when this has to be less than 0? It should be, right, it should be greater than 1. When it is greater than 1, this is negative, correct? So let me cross check that. Yes, for case 3. See, all I did is, instead of separately mentioning 3 conditions, that casing, I put it another briefcase here and put it, I'm showing you here that this epsilon I is not a single value, but this is what it would happen. Then this would be when it is beyond the margins, outside the margins, inside the margin correctly classified, inside the margin misclassified. Clear? Right. Now, what should we do now? We should write an equation at the end of the day, right? So let's call a function of as j, because I'm going to write multiple functions. I just started with j for now. I have anyway w bar is there, w naught is there. I'll just keep that. If something is required, we will write. Let us write a maximization function. What is the first term here? It should still, our goal is to maximize our margin. There is no doubt about that. So what should be our first term in our minimization problem? Sorry, in the minimization problem, when you want to maximize the margin, 1 over norm of w bar square is still intact. It is there. Now, here comes another thing. There is something else that you want to minimize also. What is it that you want to minimize? Intuitively, even if they are non-separable, the number of feature vector inside your margin you want to minimize, obviously, correct? So that function has to come here now in your optimization problem. That I have all that exercise I have done just to make ready the constraints there. I will bring that and later impose that constraint. But even before that, so I could write it as, let's say, plus some other weight I am giving. This is a trade-off weight I am giving times, let's say, I go through all points. I will impose a penalty when the point is inside. Otherwise, I will not impose that. So I put a constraint of I of xi I, because that xi I will tell me where that point is. Okay. So this is the new function. You could notice here, is this a continuous function or a discontinuous function? This is a discontinuous function. It will be, the way this is defined is xi I equal to, don't pose any penalty if it is outside your margins. Okay, that is what you want. So don't penalize this guy when he is standing outside your margins. So you make it 0 for which values? So for case 1, right? For xi I equal to 0. Here I should write I of xi I. Okay, this function, I'll, as long as he's outside your margins, don't penalize that guy. If he's inside, you penalize him. Okay, this is the term. And then this C, by the way, is not something is not a parameter that for which you optimize. You have to take a trade-off, like how many outliers you allow inside, how many you want, let's say 10%. So accordingly, based on these two, you decide what is the relative weight there. Okay, so I could comfortably close this case there with as I of w bar comma naught, and then of course there is something here, xi bar is there. Okay, those values are there for you now. Okay, that is this constraint that is coming, that is embedded here. Xi bar is there, but these are the 3 variables. Mistake not, or don't confuse that this is some parameter you are going to optimize. This is some empirically you will choose some weight based on some observations, based on some prior knowledge, whatever it is. Okay, now is that good enough? Now what else we need to do? Subject it to the constraints. That will tell you only, this will only tell you if it is inside, it is penalizing, but you need to still impose those constraints there. Correct. Now that's what you will do. Subject it to the constraints. Then you have to pose those constraints. So let us write that equation now. How does so C, by the way, C is a positive constant. It cannot take any negative value, because that's essentially a weight you are giving, and that's what you are trying to minimize. Okay, subjected to the constraint that yi into w bar transpose into x bar plus w naught, okay, minus 1 plus xi I is greater than or equal to 0. This is the constraint. I'm just taking that constraint, generalized constraint there. Make a note here. So here there is a xi I, when this is a maximization here. So while you are doing minimization, there comes here a minus sign here, correct? And when it is more, obviously your minimization problem will encourage the points, will penalize less when you have correctly classified points. So this is a small subtle thing, but it would be good if you can notice this. While how do I minimize? If you want, I will maybe first write the minimize. There is one more constraint also. Let me write that first. Can xi take negative values? The whole thing becomes a mess. It cannot take negative values. So another condition is also there. Should be greater than or equal to 0. Now let me write your Lagrangian multiplier formulation, where I have w bar, w naught, xi bar. Okay, I'll have 2 more variables for these 2 things, 2 conditions. Let me call this as lambda bar. Let me call this as another one as, let's say, mu bar. I'm writing the equation now. This would be half of norm of w bar square plus c times I equal to 1 to n I of xi I, then what should I do for this? Negative I should take, right? This is a greater than or equal to 0 is a maximization problem. Minimization problem I want. So minus summation, you go through all points. For each one, let's say you give a weightage of lambda I there for each of those constraints. And this lambda I is multiplied with yi w bar transpose xi bar plus w naught minus 1 plus epsilon I, right? That's what the weight for each of these constraints is given by, there are n constraints, lambda I is telling you the weight there. Similarly, one more constraint, this xi I cannot be less than 0. So you are trying to maximize this xi I. So that means minimization minus is another sign you will get. So another term again, I equal to 1 to n. Let me put mu I here, mu I into xi I. This is the argument that function minimizes. You have all these variables now, w bar, w naught, xi bar, lambda bar, mu bar. Okay. Then you could, as I mentioned, take some time later and notice that, as I was mentioning, this would in fact would be max once will be minimum for correctly classified things in terms of xi I. Just look at that. It is not at all difficult. Minus, so this is minus xi I here. So you are minimizing it. So xi I, based on that, you just look at it and make an interpretation there. Okay, that also will tell you. Anyway, this function is also taking care. So this function taking care that, what is this one? This term taking care. There are minimum feature vectors inside your margin. What is this function taking care? The constraints on that, similar to the constraints we had earlier. What is this is taking care? Your xi I values are always positive. That's how. Okay. Then again, this is you could again look at it into the primal dual scheme. Then this I leave it to you as an exercise for you, where you would now make an equivalent dual problem. I'll just tell you the outline. Dou L by dou W bar equal to 0, you make it. Similarly, dou L by dou W naught equal to 0. You get two equations there. You substitute them here. Then you will get rid of both W bar and W naught. All you will be left with these three variables. There it will be a maximization problem. You solve it. Okay. This I give it as an exercise to you. So please work it out. And it is there in the textbook we are following. So then cross-check your answers there. It's a good exercise. And you cross-check your answers with that. Okay. Any questions or any doubts, comments here so far? Is that clear? Or do you have any questions here? One question I could ask you is to give one of those problems. I'm giving not one question, but a set of questions I'm giving you. I could give you the whole constraint and I can ask you to formulate its dual problem. That is possible, right? That is something I could give you. Or I could give you an optimization problem in some analytical terms and could ask you to solve that also using this optimization problem. For example, consider I have a function like f of x comma y equal to x square plus y square. Okay. And how does the contours of that would look like when I have both x and y? Can I draw on the board? Is that possible? So how do you draw it on the board? Something like this. Don't ask me to draw surfaces. Already you have got exposed to the way I could draw the graphs and all. So don't ask me that. Don't venture into that. But what's the other way you could draw? Which one? Right. Very good. Isocontours. I can draw you isocontours, which you have seen earlier. Okay, those are, I'm just drawing those which have the same value, right? If x square plus y square equal to 1, circle with, that's a big mistake. It should be at the center. Okay, but nobody will be evaluating me, so it's fine. Okay, I could have x minus a whole square plus y minus b whole square also. Something like that will be there. Now, if I just give you f of x comma y equal to x square plus y square, what is the optimization problems minimization minimal value for it? What is the minimal value for it? 0. There is no fun in that, so that will not be given. Okay, so I could in fact give you some other constraint saying like an equation of ax plus by equal to 1 or x by a plus y by b equal to 1. That's the constraint if I pose you, right? Well, that's a very bad way of drawing. Let me draw something where I get a solution. Okay, this is the line I draw. Then this is subjected to the constraint that this has to be 1 equal to 1. I can give you that, right? Then what will be the solution? This where you get this cut here will be your solution, subjected to an equality constraint. This is still not an inequality constraint. Okay, this you could comfortably solve this problem by the way we did the derivatives and all, because I have given you one analytical function. This is one possibility. Okay, another possibility is I could tell you x by a plus y by b is less than 1 or greater than 1. What should I give? Okay, let us give both and see what will happen. I don't know. I'm also thinking what questions to give. So I'm putting some permutations and combinations there. Suppose if it is greater than 1, what will happen then? Any solution in this region would work out. Correct. Then in this region, which is the minimum value of that, you have to see. Hope you are getting it. If it is other way around, what is the solution? Can you tell me already? Very comfortable one. 0 is the solution because 0 is already lying there. Here, perhaps this again, this itself will be the solution there because that's the minimum here, still satisfying the condition. Okay. Take some examples like this. You work out where you first formulate it as a constraint optimization problem. The constraint could be an equality or an inequality. Okay. Then see how you solve it. Then nicely make a dual problem of it, also work it out. And that also solving should give you the same result. Okay. You just look for some, that is something I could think of the problems that I could give you. Or as we were doing it, I could give you that minimization problem in W bar, W naught, lambda, and then I ask you to give me the dual one. I could give you any equation there and can ask you to derive that. Okay, you just need to find out the derivatives of it analytically, substitute that, see what is the equation you are getting there. So those are broadly what I could see, what I can give you there. Okay, and then yeah, those are the things that I could think of right now. Something comes out, you are unlucky, I might give you, but this is for sure I will give, very likely I will give something in these lines. Okay, so be very comfortable with constraint optimization, primal dual algorithm, Lagrange multipliers, all interchangeably I'm saying these names, all those things. Then given a problem, how do you bring its dual problem? Okay, these are the using that KKT conditions. We don't need to, we never touched those guys, even their full names. We just are looking at as KKT, but that's good enough. You just minimization will become maximization. If your variables are W bar and W naught, you take derivatives of that with respect to the partial derivatives, make them to 0. The equations you substitute and get rid of those two variables there. That will give you a dual. Fine. Right. So now let us graduate to nonlinear classification now using SVM. We are done now with linear classification for both separable and non-separable. The last topic that we would see under the umbrella of SVM is for nonlinear classification. Okay, I will not deal with nonlinear, non-separable and all these things. We had enough of permutations and combinations. The last one we would see is nonlinear classification. Okay, so assume that, again, maybe this way of drawing is convenient. I have some points here. Maybe I would just first draw my this thing first, and then I'll do that. I have few points here. This another class points I have here, similar to XR problem. Okay. Then I have here some point, again the same class, the first class which is inside was repeating here. Okay, good enough. This is my x1, x2. Don't ask me x1, x2 negative. Why will it get in? Something like that. Assume that I have it. Now I ask you, suppose if I ask you to solve this problem using SVM, do you have any ideas on how to solve that? I have given you so clearly this. A very special case I have given you. With whatever type of SVMs that you know, can you translate that? Can you do something and still solve this problem with that? Very good. So I think you are mentioning in similar lines, x square you take, right? You take, instead of taking x and x1 and x2, you look at in the space of x1 square and x2 square. That's what you are saying, right? That's what you intend to say. So then what will happen? X1 square plus x2 square, right? X1 square plus x2 square, this thing versus this thing, okay, versus this, then you will get a linear, you could end up with a linear thing. Okay, let us keep things simple. This also I'll remove, otherwise still I can do, but let us keep things simple. Okay, just I have something like this. This is you cannot draw a line. Nevertheless, you can go to x square and x2 square space, and then they are linear. Okay, well, this is a very tailor-made problem for us to extract an answer from you, but not all the time circles don't expect circles in life. Of course, same things may repeat, but in problems you could get different patterns there. So what could you, the another generalization of this x1 square and x2 square? You are free to go to higher dimensional space, let's say. Then what will you do? You go to all of these things. What you can do? a1 x1 plus a2 x2 plus, or you have terms like x1 x2 x1 x2 x1 square x2 square, all possible things. You go from a two-dimensional space. I go to a space 1 2 3 4 5. I don't know if constant also makes sense. You take that also if something makes sense. I will go to 6-dimensional space. Suppose then if there is some quadratic way of separating things in the higher dimensional space, they could be linear. We have seen that to an extent while we are discussing about the XR problem, right? In multi-layer neuron or two neurons or multiple neuron model also. So the then if this problem somehow turns out to be a linear problem here, I can go back to my SVM. But what is the problem here is, you don't really know, is this by the way, is this the only way? Polynomials is not the only way. There could be some other nonlinear transformation which we don't know, transformation we don't know. Even if I give you transformation, until and unless I draw and see, whether I don't know whether the transformation makes them linearly separable is what I do not know. But there is a very nice property that you could figure out from SVM, that you can do something without really applying any transformation, but assuming that this transformation of a polynomial transformation would give you this. You don't really have to apply the transformation, but you could still do some classification there. That is possible. This we will see that part now in how this can be done. So this is what we will do. By the way, just I got reminded, this xia you are mentioning about the slack variables in the last class. So that xia is called as this slack variable or slack term that you are asking in the previous class. Okay, that suddenly popped up in the mind, so I just came back there. Okay, I just summarize what I told so far. Suppose you are having your SVM algorithm, but you have your feature vectors are not linearly separable. But if you can manage, one way is if you know a particular transform, applying which you go to higher dimensional space, it is possible. I'm not saying it is always possible. It is sometimes at least possible that they can be separable in this higher dimensional space after applying a linear transformation. Is the point so far clear? If so, we will build one more module that is required to comprehend things. Now, let me move on from here. Suppose I have x1, x2. I am in the space of a two-dimensional feature vector. x1, x2 space, I am there. Okay. Let me call this as x bar. Now, I moved from here. Now you got the idea on why I want to move. If I move, my hope is that I will go to higher dimensional space and I become linear. That is my hope. Okay. Right. So that's why I want to go to higher dimensional space. Let's again take a very specific example to get a feel of it. Let's say what is my higher dimensional space here is x1 square, square root of x1, x2, x2 square. Okay. Now, I want to do, let's say, yi bar transpose into yj bar. That means I have this feature vector. I have xi bar and xj bar here. Okay. I plotted all these xi bar and xj bars. I have roamed around that and seeing from all view angles, and I see I cannot fit any linear line there. Somebody told me that this will fit. You go to three-dimensional space and see it fits a linear line. Then what I did is, for all these xi bar, these are two feature vectors, let's say I have taken. Now yi bar and yj. Now again, recollect the equation we have written for support vector machines. Where were they exactly? What is the computation that we were doing with the feature vectors in our final equation? That too, dual problem. There is only one operation that we are doing with these feature vectors. What is that operation? That was the last class we did, ended our last class there. Look at the equation that we have written in the last class, end of last class. Feature vectors, there is only one operation we were doing. What is that? No. My question is, there is one operation we were doing on this feature vectors. Look at the equation that we have written at the end of last class. Very good. What is that? What is that? Is referred to as that operation? Inner product, dot product. It is only the dot product is the only operation you need to do to solve the support vector machine problem. Clear? Now let's attempt that now. Okay, let's do a dot product of yi bar and yj. Okay, this is equivalent to saying yi bar transpose times yj bar. This is the only operation that I need to do. If you look at what we did in the last class, that's what you have to do in the SVM thing. Okay, same thing happens in the, I have not written the dual problem. You again realize there, even for linear non-separable, this is the only operation you have to do with them. Okay, can you tell me what is this value? Okay, well, I and j are there, put them here. Okay, when you put the equations, let's say I write yi bar transpose as, how should I write? x1j, x1i, okay, x1j square root 2 times x1i, x2i, x2i square, this whole thing multiplied by, now I have j here, so x1j root 2 times x1j, x2j, x2j square. I missed the square here. Okay, that's all. See, these are two different values, x1, y1, x2, y2. I don't know how to write because I have gone to already x1, x2 are there. So I'm just giving one more subscript there. Okay, nothing extraordinary I'm doing there. So what is the value there? Can you tell me the value now? x1i square times x1j square plus 2 times x1i, x2i, x1j, x2j plus x2i square, x2j square. Okay. Now, this is what I did between these transformed variables. What is the dot product for x1 and xj? Can you please write that? What I want now is x1 bar, should I write xi bar? I should write comma xj bar dot product, which is equivalent to xi bar transpose times xj bar. Okay, what will I get there? Can you help me out? xi1 times xij plus xi2 times x. I'm writing some, I'm missing something. x1, x2i gonna, yeah, x2i times x2j here. Okay, x2i times x2j. Yeah, it is just like writing on one side xi means x1i, x2i. Okay, here this is x1j, x2j. That's all I'm doing there. Okay, that multiplication. Now, next question to you is, can you help me on if it is possible to get this expression from here? Is it square of that will give you that expression? Okay. Okay. So what I will do here is, this is not, now what I could write here as a result is yi bar, yj bar, the dot product of it is equivalent to xi bar, xj bar dot product whole square. It might look so trivial, or what is that we are achieving here? It is telling you that under certain conditions, again, we leave all scientists and their theorems away, just we take whatever is required here, but still it's good to acknowledge there is some theorem called as Mercier's theorem. Again, I don't know whether apostrophe is there or not. Mercier's theorem is there. So before anyway coming to that, what I want to say is, there are quite a few instances where the dot product in the higher dimensional space can be written as a function of the dot product in the lower dimensional space. Please pay attention to every word, every term I am using here. I have moved from here to a higher dimensional space. See, finally what I should do in my SVM problem, I need to find out a dot product between each variable. We have summation i1 to n, j1 to n, lambda I, lambda j. Then if you see xi bar j transpose into xj bar will be there. So every possible combination, all I am doing is a dot product. I have to, when I go into a higher dimensional space with the hope that that is where the world is ideal and I turn into a linear classifying problem. I turn into a linear classification problem. There I need to find out a dot product in that. What this is saying is, well, there are quite a few instances. The conditions, he will tell us the conditions. We don't worry about that. Okay, he tells you the conditions under which this is possible. What is possible is, you take a function of dot product here in your lower dimensional space. Okay, and then these two problems are equivalent. Now again, why it is important that you correlate it with SVM. That's why I'm again and again coming back. At the end, even once you go to higher dimensional space and represent it, to find out the lines, you take a dot product of them. Now, rather, what you do is you still remain here, but you take some possible commonly widely used means widely making sense functions here on the dot product here, and you don't really have to move into higher dimensional space. You don't even know how many dimensions are there here. For example, this has been 3-dimensional, but there are, this is for illustration, I have taken a small example, but you never know to how many dimensional space you have to go. What is the function you don't have to go know? Only thing you will do is you will use a kernel of x on xi bar and xj bar. This kernel could be a polynomial kernel, where, as I have written there, a1 all combinations of xi square, xi bar, xij, xiij, you take whole power 2, 3, 4, you can go. It could be also a Gaussian like kernel, which is referred to, the name of that is radial basis functions, which is, you might have already seen that it is exponential of norm of x bar minus z bar square whole by sigma square. So assume that these are the two you are giving as inputs to the kernel. So I have written here x bar comma z bar. So all you do in your equations, earlier equations, you replace the dot product of x bar comma z bar with this kernel k of x bar comma z bar and take different possibilities. Okay, hope it is clear. I will write some functions also. I'm in the interest of time now, I'm stopping.